Good morning, AP Physics students. I miss you. I'm here to give you some quick guidance regarding your session today with Mr. Brennan. I'll keep it brief. The learning objectives include investigating the variables that affect the motion of an object as it travels in a circle, and to review the angular velocity calculation. So I'd like to quickly go over the warm-up, the exit ticket that I asked you last class for our warm-up, and then give you some direction for your circular motion lab. That'll go into the second section of your notebook. You might spend time brainstorming and checking in with your very own physics guru who you have accessible to you today. That's Mr. Brennan. And then work through collecting your data. You might start the pre-lab questions in class, but if you don't get to them today, you can finish them up remotely. So on Wednesday, I asked you, how fast does a car tire spin? Blah. And the question gave you a radius and a linear velocity. So I can write down the knowns. My radius is 0.3 meters. The velocity is 15 meters per second. They're asking for angular velocity. And you can get a little stuck here because the equations we have, our rotational angle equation is the ratio of arc length divided by the radius. And you can see we don't have all the variables here to solve for that. And then we also know that the omega, which is our angular velocity, is equal to the rotation angle divided by the time. And again, we don't have these variables. So what do? We call on our equation for velocity, which is the change in the arc length divided by the time. If you imagine yourself running around a circular track, you're carving out a certain distance in a certain amount of time. This is where this equation comes from. We spoke about that on Wednesday. And the change in the arc length can be solved from this equation, where you rearrange this equation to get the change in S is equal to R times the change in theta. So I've popped out the change in S and I've substituted in those variables. We're getting a little closer here because now we have the radius represented in our expression, but we still don't have theta. So what we can do is we can remove this R from the expression. So we pull out R times the change in theta divided by time becomes equal to the velocity. And hey, look at this. This expression is represented by angular velocity. So we can get linear velocity is equal to the radius times the angular velocity. And this equation looks promising because we have these values here. So I will take this equation, pop it up here, rearrange to solve for angular velocity, and end up with an answer of 250 per second, or 250 radians per second. All right, so today's goal includes circular motion lab. I'm estimating that you might partner up and engage in a 5-minute brainstorm. You've already done a lot of your brainstorm remotely and with each other on Wednesday. Check in with Mr. Brennan, run it by him, see if he has any ideas or suggestions if you need additional tools. I'm sure he's willing to help you access that equipment. And then collect your data today. This is your only day that you will collect data. And don't worry if you get stuck. Like, if you can solve for some of the variables, go for it. If you're getting stuck, bring those questions to class on Monday and Tuesday. And again, if you get to the pre-lab questions, great. If not, you can finish remotely. That's it. Thanks so much. Have fun. Bye.